Let's start the article number 4 of chapter number 1, that is law of conservation of linear momentum. So, what is the necessary of studying this law of conservation of linear momentum? Because we have studied the topic center of mass, in which if the resultant force acting on the system is zero, then what happens? The resultant force means the effect of internal force as well as the effect of external force. Therefore, F vector is equals to dP vector divided by dt, and this is also equal to 0, and hence the momentum P is constant, or we can say the total momentum of the system of particles. Suppose there is a system of n particles. So this total momentum is remaining constant, and so we know the meaning of total momentum of the system is constant. That means this momentum is conserved in the system, and hence I am writing here one important statement, that if the resultant external force acting on the system is constant or is zero, because we have started our theory with this assumption only. So when this force acting on the system is zero, then the total linear momentum, see this linear word which I am using over here is for a simple type of motion. And this total linear momentum of the system remains constant, and this particular statement which I have written over here is known as the law of conservation of linear momentum. So this is the statement. Now, if there is an absence of resultant external force, that means whenever there is F is equals to 0, at that time the momenta of individual particles, means P1, P2 up to Pn, may change individually, but their sum, means their addition, P1 plus P2 plus so and so, will not change. P1 plus P2 plus so and so Pn will not change. Also, if you consider one more thing, that the total change in the linear momentum is zero, because this addition is not changing. This is a vector addition, remember. Momenta or momentum, you can write anything. Then this momentum remains constant, means this value will remain constant. Now, one important example which is related to this total linear momentum constant you can study as, suppose the gas molecules in a closed container move randomly. Inside the container. So, during the atomic collision, we have seen the collision effect. The molecules with the wall of the container, their momentum changes individually, but there is no change in the total momentum. So, their total linear momentum will be constant, and hence we can say that not in this particular gas molecules. Also, you can take any example of either solid and liquid or any plasma ionic molecule. Then in all that substances, you will find out that there is existence of law of conservation of linear momentum, and hence I can write down the law of conservation of linear momentum is universal, and also it is fundamental. So it can be asked that prove that the law of conservation of linear momentum is universal and fundamental. So it is very easy, and this law is valid for the big system such as planets, galaxies. Similarly, for small systems, this is also valid. So this is the validity. Also for small system, it is valid. For small system, I can consider electrons and protons. So this law is also very important because it is applicable for any type of particle. Now, if you remember one equation which we have derived, that Newton's second law of motion and the motion of center of mass as F is equals to MACM vector. Therefore, this is M. What is A? It is the time rate of change of velocity. So, dvcm by dt. And when this resultant acting force is zero, then what happens? At this particular point, the center of mass acceleration will be zero, and due to this, the velocity of the center of mass will be constant, and hence the momentum is constant. Now, these 2 points you have to remember, and this is very important also. And if you see, in the absence of external force, the center of mass of the system remains stationary, which means that whenever the resultant acting force is zero, then the center of mass will remain stationary, and if it moves with constant velocity, then it will be also appeared as stationary. So these two possibilities are exist when the resultant acting force is zero. Now we will also see one illustration in which there is a chemical bomb is stationary and whenever it is blasting. So let's go through the illustration. Let us consider an example of a chemical bomb as seen in the figure, in which first of all I am considering this bomb as stationary or static. Then I am trying to find out its initial momentum and kinetic energy. So at this case, its initial momentum will be zero. Also, as the momentum is zero, then its kinetic energy will also equal to zero. Now, when the bomb explodes, then their particles or their portions will be thrown in the air. And also, the direction and the magnitude of these particles will be in a condition that its total linear momentum will be zero. Therefore, P1 plus P2 plus so and so. Suppose the bomb explodes in n particles. So this total momentum will be 0 and this P1, P2, what we are considering as the momentum of first particle, but now for all the values I am using the same word as momenta fragment. Or momenta of fragment. So this is the general word you can use. If we move further, then what the other characteristics are seen in this particular event? So the center of mass of the system of the fragment will be remain at the same point, as it was located before the explosion. So here the quality as center of mass remains constant. So there is no change either in the position or in the magnitude of the center of mass. Now, if we see the kinetic energy after the explosion, then this kinetic energy will be not equal to 0. What is the reason behind that? Because after the explosion, the fragments are having certain velocities with definite mass in the particular direction of displacement. So there is no kinetic energy. We can say it is 0. Now the energy of the system is changed, and so as the energy is changing, we can have the quantities like work, energy, power, and etc. So, the kinetic energy of fragments is not zero, but is there any change in the kinetic energy of a bomb itself? So we can say there is no change because the internal energy was converted into the heat energy, and the remaining part was converted into the kinetic energy. So here the energy is consisting of two types. The first one is of heat energy and the other one is of kinetic energy. And using these two energy, some kind of work is done over the bomb, and so work is also taking place here, energy is also taking place. So this particular event is leading us to the work energy theorem. Now, have you ever analyzed the direction of motion of the center of mass of the fragments of the bomb after the explosion? So, from this figure below, you can easily analyze that event. In the above event, we have considered that the bomb was in stationary, but suppose the another case I am taking over here, if the bomb was moving with constant velocity and then it explodes. So what happens? So according to the conservation of linear momentum, its fragments would have or they would move in the direction such that the total momentum should be conserved and the change in the momentum should be zero. And the center of mass would move such that its original velocity is maintained. So here VCM is maintained towards the journey after explosion and before the explosion. So this is the end of the most important theory of your chapter, which is law of conservation of linear momentum, and we will solve some examples related to this particular theory.